Greetings, and thank you for joining us on Sleep Science Top 1. This evening, we shall embark on a soothing fireside journey into one of the most remarkable concepts in the realm of science. The unseen tapestry of space-time forms the very foundation of our universe. It is a realm where celestial bodies ignite and orbit, a place that has witnessed the rhythm of every human heartbeat throughout time. The bending of light around galaxies and the slowing down of clocks reveal how space-time intricately weaves the universe together, showcasing a tapestry that is both elegant and inspiring. It bends around matter, elongates as the universe unfolds, and resonates with the waves created by colliding black holes. The air surrounding you is a part of its grand design. This evening, the journey will unfold as we explore the intricate layers, the nuances, and the hidden glimmers within this tapestry. They would transcend the basic concepts of time and space, catching a glimpse of a universe that flows as a singular, vibrant entity. If these serene journeys resonate with you, consider liking, subscribing, or sharing your thoughts below. It helps guide others here too, one weary spirit at a time. For the moment, all that is required of you is to unwind. As the breathing slows and the shoulders soften, the day begins to fade, allowing the mind to unwind into the vast and endless cosmos. Let us commence. The essence of space-time weaves the very structure that binds the universe in unity. The background stage is not merely a setting for events to unfold. It is the fundamental framework that shapes the existence and movement of everything in the universe. Each planet, each star, and each atom exists within it, influencing it, while also being influenced in turn. It weaves together 3 dimensions of space and 1 of time, forming a unified 4-dimensional continuum. In the presence of mass or energy, this continuum bends, giving rise to what we perceive as gravity. When it is devoid of content, it retains its smooth and flat appearance. Even that seemingly empty space possesses characteristics, able to stretch, compress, and carry waves. In the absence of this cohesive element, the significance of distances and durations would fade, and the existence of consistent laws of motion would be rendered impossible. The unseen backdrop and the engaged player, the subtle structure that maintains the universe's harmony from the tiniest atom to the expansive network of galaxies. Time and space exist as interconnected elements. For centuries, space and time existed as separate entities, one delineating the location of objects, while the other marked the moments of events. Einstein's work revealed that they are intricately linked, essential components of a unified whole. The movement of an object through space impacts its experience of time, while the flow of time can alter the way distances are perceived. This indicates that a clock held by a moving observer will not tick at the same rate as one that is stationary, and rulers in motion will seem shortened to those observing. The 2 quantities merge into a single system, harmonizing to ensure that the laws of physics remain consistent for all. Every event in the universe can only be completely understood by considering both its position and its moment, creating a 4-dimensional coordinate. This revelation transformed the field of physics, uncovering a reality that is intricately linked in ways that surpass our ordinary perceptions. Einstein's insight transformed the comprehension of reality for all time. Einstein's theory of relativity transformed the understanding of motion, distance, and time. Prior to his research, it was believed by scientists that these values were fixed and applicable everywhere. Einstein understood that measurements are influenced by the observer's state of motion, and that there must be a consensus among all observers regarding the speed of light. This straightforward principle compelled all else to realign. As time drags for the clocks in motion, space compresses in the direction of travel, and the concept of simultaneity shifts, revealing its relative nature. His insight brought together mechanics, light, and gravity into a single, elegant framework, guided by geometry instead of unseen forces. This framework has stood the test of time for over a century, consistently proving its worth. Every experiment, from the bending of starlight to the precise timing of satellites, affirms this truth. Einstein's equations transformed previous certainties into interconnected relationships, revealing that reality is inherently dynamic, adaptable, and influenced by the contours of the space-time it occupies. Gravity is not merely a force, it represents the curvature of space-time. The phenomenon we perceive as gravity is not a force pulling through the void, but rather the inherent movement of objects, tracing curved trajectories within the fabric of space-time. Large celestial bodies like planets and stars warp the space around them, causing other objects to navigate along the most direct paths within that bent terrain. When a ball is dropped, it is not being pulled down by an external force. Rather, it is moving along the path, shaped by the gravitational field generated by Earth's mass. The Earth rises to meet it, instilling a feeling of heaviness. High above, satellites glide through the void, perpetually descending along trajectories that never truly touch the ground. Even light bends as it approaches massive objects, tracing those very curves. This geometric explanation transformed the concept of gravity from a mysterious, invisible force into a revelation of a universe where motion and structure exist as a seamless, elegant system, molded by mass and energy. Matter instructs space-time on its curvature, while space-time guides matter in its movement. This phrase, introduced by physicist John Wheeler, encapsulates the essence of general relativity. The existence of matter and energy shapes the curvature of space-time, and this curvature, in turn, governs the movement of all entities within its realm. The connection is reciprocal and ever-evolving. As mass accumulates, it distorts the geometry around it, forming wells and ridges that shape the paths of particles and light. The motion and distribution of matter continuously adjust those shapes. This feedback loop influences the paths of celestial bodies, the rise and fall of ocean tides, and the very growth of the universe. Einstein's field equations articulate this interaction with precision, connecting the universe's contents to its geometry through a series of elegant, interwoven mathematical relationships. The outcome reveals a harmonious cosmic structure, where every element operates with purpose and intention. Each journey, each stumble, and each cycle emerges organically from the conversation between substance and the very fabric of space-time. Space-time possesses the ability to be stretched, twisted, and warped. The structure of space-time is fluid and adaptable. It has the ability to stretch with the expansion of the universe, twist around rotating masses, and warp in the presence of dense regions like stars or black holes. As galaxies drift apart, it is not due to their movement through space, but rather because the space that separates them is expanding. In the vicinity of a spinning black hole, the intricate dance of space-time pulls surrounding matter and light into mesmerizing, swirling patterns, a phenomenon known as frame dragging. In laboratory and astronomical observations, light from distant stars shifts and bends as it traverses different gravitational fields, unveiling the unseen outlines of space-time. These distortions can be quantified, anticipated, and are essential to understanding the nature of the universe. The capacity of space-time to bend leads to phenomena such as gravitational lensing and the graceful movement of planetary orbits, demonstrating that the universe is constructed on a dynamic, adaptable geometry. The presence of mass causes time to flow more slowly. Time flows unevenly across different realms. In the presence of massive bodies, the passage of time is altered, causing clocks to tick at a slower pace than those situated at a greater distance. This phenomenon, recognized as gravitational time dilation, has been accurately measured through the use of atomic clocks, both on Earth and in orbit. A clock positioned on the surface of our planet ticks at a slightly slower pace compared to one in a satellite, necessitating adjustments for GPS systems to maintain their precision. The explanation resides in the curvature of space-time. As an object descends further into a gravitational well, the passage of time for it slows in comparison to those observing from afar. This is a tangible reality, one that can be quantified and observed. In the vicinity of black holes, the contrast reaches remarkable levels. To a distant observer, it seems as though objects descending toward the event horizon come to a standstill, while for the object in motion, time flows, as it always does. The force of gravity transforms not just movement and the fabric of space, but also alters the fundamental cadence of time. The quicker one travels, the more time seems to drag on for them. The very act of motion influences the passage of time. In the realm of special relativity, it is understood that as an object approaches the speed of light, time for that object appears to slow down when viewed from the perspective of a stationary observer. This phenomenon is known as time dilation, and it has been confirmed through numerous experiments involving fast-moving particles and accurate atomic clocks on high-speed aircraft. For instance, muons generated in the upper atmosphere exhibit a significantly longer lifespan when moving at speeds close to that of light compared to when they are stationary, precisely as anticipated. To the travelers, everything seems perfectly ordinary. In their perspective, time progresses as it always has. To those watching from the outside, it seems as though their clocks are ticking at a slower pace. Should a spacecraft achieve velocities close to that of light, its travelers could find that only a few years elapse for them, while centuries unfold on Earth. The connection between motion and time indicates that each observer's perception of duration is unique. Each viewpoint is influenced by pace and context. The speed of light remains constant, regardless of the circumstances. Regardless of your speed or the path you take, the measurement of light's speed in a vacuum remains constant and unchanging. This constancy serves as a cornerstone of modern physics, underpinning the very functionality of relativity. It signifies that both space and time are compelled to adapt in accordance with velocity, adjusting, compressing, or expanding to maintain the constancy of light speed. Endless experiments have validated this, ranging from the interferometer tests of Michelson and Morley to contemporary measurements using lasers and particle accelerators. The outcome reveals that the behavior of light imposes a fundamental boundary on information, energy, and motion. Nothing can escape its grasp, and all that moves draws near in unique ways, influenced by its own energy. The universal consistency enables the equations of physics to remain valid across the cosmos, guaranteeing that the same principles govern everything from the tiniest atom to the most distant galaxy. The universe, in all its complexity, finds coherence through the unwavering constancy of the speed of light. The constant speed of light serves as the foundation for all physical laws. As it remains constant, every observer in the universe is able to articulate motion, energy, and time in a coherent manner. It establishes the relationship between mass and energy, governs the flow of information, and outlines the framework of cause and effect. Without it, the essence of time and space would become meaningless, and the core principles that govern the universe would unravel. The speed of light weaves together electromagnetism, relativity, and quantum theory into a unified framework. It influences the speed at which signals travel to us from far-off stars, as well as the duration we must endure before experiencing cosmic occurrences. Even the definitions of the meter and the second are influenced by it. The constancy of light serves as a silent metronome of reality, weaving a universal rhythm that connects the tiniest particles to the most distant corners of spacetime. The GPS system would falter without the necessary time adjustments provided by relativity. Modern navigation systems rely on satellites that orbit Earth, each one fitted with atomic clocks that measure time with remarkable accuracy. However, these clocks do not tick at the same pace as those on the ground. The satellites traverse the vastness of space at remarkable speeds, leading to a fascinating phenomenon where their clocks tick at a slower pace, a consequence of the principles of special relativity. Simultaneously, they find themselves at a greater distance from Earth's gravitational influence, resulting in their clocks operating at an accelerated pace as described by general relativity. The cumulative impact leads to a daily timing deviation of approximately 38 microseconds. Despite its small size, this discrepancy could lead to location errors spanning several kilometers each day if left unaddressed. Engineers consider these relativistic differences to ensure that the time on satellites and the time on the ground stay in sync. Every time your phone determines your location, it subtly employs Einstein's theories to correct for these distortions, demonstrating that even the most commonplace technology must yield to the peculiar bends of space-time. Time flows more swiftly on a mountain than it does in a valley. The passage of time varies subtly based on one's position within Earth's gravitational field. A clock perched atop a mountain ticks away moments with a slight haste compared to its counterpart, nestled in the valley below. This phenomenon, known as gravitational time dilation, arises from the way gravity influences the flow of time. As one ascends, the gravitational force diminishes, and the passage of time accelerates. The impact is remarkably subtle, yet quantifiable through the use of atomic clocks. In one experiment, scientists positioned two synchronized clocks at different heights to a few meters apart and observed a notable difference in their ticking rates. Throughout a human lifetime, the head experiences a slight acceleration in aging compared to the feet. Even the smallest distinctions hold significant importance in the realms of technology and science. It is confirmed that gravity and time share a profound connection, with the experience of each passing second intricately influenced by one's position within the curvature of Earth's spacetime. The bending of light uncovers the contours of spacetime. As starlight approaches a massive object, the trajectory it follows bends gracefully. The bending occurs not due to an external pull on the light, but rather as a result of the very structure of spacetime. In 1919, astronomers witnessed this phenomenon during a solar eclipse. It was observed that stars seemed to be slightly out of place from their typical positions when their light traveled near the sun. The measurements aligned perfectly with Einstein's predictions, offering one of the earliest validations of general relativity. In the present day, researchers harness this phenomenon of light bending to explore the unseen framework of the cosmos. Through the observation of light from far-off galaxies being bent by clusters of matter, astronomers are able to chart areas rich in dark matter that remain completely invisible. Each distorted image, observed in the vastness of deep space, serves as a direct reflection of the curvature of spacetime, illustrating that gravity influences not only motion, but also the fundamental trajectory of light itself. Gravitational lensing transforms the fabric of space into a vast cosmic magnifying glass. As light from a distant galaxy journeys through the cosmos, it encounters a massive object, like a cluster of galaxies. The gravity of this cluster bends and focuses the light, creating a captivating phenomenon. The outcome manifests as a phenomenon recognized as gravitational lensing. Depending on the alignment, arcs, rings, or even multiple images of the same background object may emerge. This natural magnification enables astronomers to explore galaxies that would otherwise remain too faint or distant to observe. It further uncovers the arrangement of dark matter, which constitutes the majority of the mass within the lensing cluster. Researchers have the ability to examine the distortion of light, allowing them to create an intricate map of the unseen structures that influence the universe. Gravitational lensing stands as a remarkable instrument in contemporary astronomy, reshaping spacetime into an expansive telescope that reveals the universe's most concealed and far-off domains. Black holes represent areas where the fabric of spacetime undergoes a profound collapse. As a massive star reaches the end of its nuclear fuel, the relentless force of gravity may compress its core to an extraordinary density, ultimately giving rise to a black hole. In this state, the curvature of spacetime becomes so intense that not even light can escape its grasp. The boundary of the region, known as the event horizon, signifies the edge of what can be seen. Beyond it, gravity exerts such an overwhelming influence that the familiar concepts of space and time begin to dissolve. At the center, resides a singularity, a point where density and curvature reach infinity, causing our established laws of physics to falter. From afar, one might witness an object descending toward a black hole, seemingly decelerating and diminishing, perpetually on the brink of crossing the horizon. For the octet, time moves at its usual pace as it delves deeper within. Black holes are not mere voids in space. They are areas where space-time has undergone a profound collapse into a state defined solely by gravitational geometry. The boundary surrounding a black hole is referred to as the event horizon. The event horizon envelops each black hole, signifying the threshold beyond which escape is no longer feasible. It is not a solid surface. Rather, it represents a boundary in space-time where the force of gravity matches the speed of light. Anything that crosses it, be it matter or radiation, becomes ensnared for eternity. From a distance, one might notice that objects descending toward the horizon seem to decelerate, lose their brightness, and become suspended in a moment that stretches endlessly. From the perspective of the falling object, the journey unfolds seamlessly, devoid of any remarkable occurrences. According to quantum theory, it is predicted that faint radiation emanates from just above this region, referred to as Hawking radiation, leading to a gradual loss of mass in black holes. The event horizon stands as the juncture where relativity and quantum mechanics converge, marking the limits of our current comprehension. It represents the cosmic boundary between the realm of knowledge and the mysteries that will forever dwell in the shadows. Within the depths of a black hole, the very fabric of space and time undergoes a profound transformation, exchanging their fundamental roles. Inside a black hole, the bending of space-time reaches such intensity that the normal separation between space and time ceases to exist. Crossing the event horizon transforms the very essence of motion, altering the fundamental principles that govern it. Upon entering, the progression through time leads unavoidably toward the singularity at the core. There exists no route that diverges from it, for every conceivable direction converges inward. To an outside observer, anything that falls in seems to come to a standstill at the boundary. Yet for the object in motion, the descent proceeds as usual. This reversal reveals that time and space are not rigid constructs, but rather adaptable elements of geometry, influenced by gravity. The singularity is not merely a point in space. It represents a moment in time that all within its grasp must ultimately encounter. Within the depths of a black hole, the familiar laws of physics dissolve into enigma. Space-time can undulate, much like the surface of a pond. Enormous entities like black holes or neutron stars can disrupt space-time with such intensity that waves propagate outward at the speed of light. These ripples are known as gravitational waves. In 1916, Einstein made a prediction about their existence, yet for almost a century, they eluded detection due to the minuscule nature of their effects. The subtle shift caused by the gravitational wave alters the distance between objects by an amount even smaller than the width of a proton. In 2015, scientists made a groundbreaking discovery as they utilized instruments finely tuned to detect these subtle distortions. The signal emerged from the collision of two black holes, a cataclysmic event occurring over 1 billion light-years distant. Gravitational waves provide a means to witness cosmic events that are completely devoid of light. It is demonstrated that space-time is not merely a static backdrop. Rather, it is an elastic fabric that vibrates, conveying the narratives of distant cataclysms throughout the universe, like ripples on a vast cosmic ocean. Those ripples are referred to as gravitational waves. Gravitational waves represent the ripples that propagate through the fabric of space-time, occurring whenever massive bodies shift or collide. They exist not as sound or light, but as ripples woven into the very fabric of the universe. As they traverse Earth, they subtly stretch and compress space, changes so minute that only the most sensitive instruments can detect them. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, achieved its first detection. The signal emerged from the merging of two black holes, validating a prediction that had stood for a century. These waves have ushered in a completely novel realm of astronomy that engages in listening rather than observing. Through the examination of their shapes and frequencies, researchers are able to ascertain the masses, distances, and spins of their origins. Gravitational waves unveil events that remain concealed from every telescope, including black hole collisions and neutron star mergers, providing a unique perspective to observe the universe through the very fabric of space-time. Gravitational waves from colliding black holes have been detected. As two black holes dance around one another, they emit gravitational waves, shedding energy in the process. As they drew closer, the waves intensified and became more frequent until the black holes ultimately merged in a spectacular burst of gravitational energy. In 2015, the first of these signals was detected by scientists after it had journeyed over 1 billion light-years to arrive at Earth. The data unveiled a captivating tale of two black holes entwining in a cosmic dance, ultimately merging into a singular, more massive entity. This event unleashed an astonishing amount of energy in an instant, surpassing the total energy output of all the stars in the observable universe combined. With every new detection that follows, unique insights emerge regarding the masses, spins, and distances of these cosmic giants. By listening to gravitational waves, astronomers delve into the universe through the very fabric of gravity, revealing a groundbreaking method to investigate events that remain hidden from direct observation. Each collision reverberates through the very essence of the universe. As two colossal entities clash, the fabric of space-time reacts, sending forth waves that extend endlessly into the cosmos. As these gravitational waves travel at the speed of light, they stretch and compress the very fabric of space in their wake. Even now, faint echoes of ancient collisions ripple through you, subtly altering the distance between atoms by less than a fraction of a proton. Instruments like LIGO and Virgo possess the remarkable ability to sense these tiny tremors, enabling scientists to piece together the cosmic events that gave rise to them. Every signal serves as a unique imprint of a far-off catastrophe, like the merging of black holes or the collision of neutron stars. These observations reveal a universe that is vibrant and ever-changing, brimming with perpetual motion and energy. The cosmos resonates with a subtle symphony, where the gentle cadence of gravity weaves through the infinite expanse of space-time, creating ripples that echo endlessly. Time dilation has been observed in airplanes. Einstein's prediction regarding the phenomenon of moving clocks ticking more slowly than their stationary counterparts has undergone direct testing. During the 1970s, researchers positioned atomic clocks on commercial flights, sending them on journeys around the globe, while their identical counterparts stayed on the ground. Upon comparison, the flying clocks revealed subtle variations in elapsed time, aligning perfectly with Einstein's equations. The interplay of motion and altitude played a significant role in creating the effect. The increased speed led to a slowing of time, whereas the diminished gravity at higher altitudes resulted in time flowing more swiftly. The outcome aligned seamlessly with the forecasts. This experiment revealed that the principles of relativity influence the flow of time, extending beyond the realms of black holes and stars to our daily experiences. Modern technology, encompassing satellites and navigation systems, relies on these adjustments. Each flight subtly reveals the malleability of time, shifting in perception based on velocity and the pull of gravity. Even the head experiences the passage of time more swiftly than the feet. The phenomenon of gravitational time dilation influences your existence with each passing second. Due to the fact that your head is positioned slightly farther from the center of the Earth than your feet, it encounters a weaker gravitational force, resulting in time flowing more swiftly in that region. The distinction is minuscule, merely a few billionths of a second across a lifetime. Yet it has been accurately measured with atomic clocks, positioned at varying elevations. In experiments, it has been confirmed by scientists that even a height difference of a few centimeters can influence the rate at which time flows. This revelation illustrates that the effects of gravity extend to time itself in all places, not solely in the vicinity of massive stars or black holes. This also implies that time varies not only across the globe, but also within an individual entity. In a gentle gradient of time, one exists where each heartbeat unfolds in a moment distinct from the last, subtly shaped by the pull of Earth's gravity. Spacetime exists in 4 dimensions, yet our perception is limited to just 3. The universe is composed of 3 spatial dimensions: length, width, and height, along with a 4th dimension known as time. Collectively, these elements create a cohesive framework referred to as spacetime. The spatial dimensions are experienced freely, allowing movement in all directions, while time appears to flow in a singular manner. Physics reveals that space and time exist as interconnected elements within a single continuum. Each event possesses a distinct place and time, intricately linked and unable to be separated. 2 observers, each navigating through the vastness of space in their own unique ways, will find themselves at odds regarding the flow of time. Nevertheless, both will articulate the same reality. The concept of relativity brings together the 4 dimensions within a cohesive geometric framework, illuminating the principles of motion, gravity, and causality. Even though direct visualization of 4 dimensions eludes us, the elegance of mathematics unveils their intricate harmony. The universe exists not as separate entities of space and time, but as an intricate, unified tapestry, constantly in motion. The 4th dimension is, in essence, time itself. When one speaks of the 4th dimension, it is not an unseen direction in space that is being described, but rather time itself. Each event in the universe unfolds at a particular location and a precise moment, necessitating 4 coordinates for a complete definition. This perspective reshapes how we perceive movement. The journey through space intertwines with the passage of time, as both elements exist within a singular framework. In various states of motion, observers will perceive this 4-dimensional reality in unique ways, encountering different interpretations of what they refer to as now. Considering time as a dimension provides insight into the relativity of simultaneity and clarifies how cause and effect maintain their consistency, despite variations in measurements. The 4th dimension is neither mystical nor abstract. It serves as a fundamental element of the geometry that unites the cosmos, linking each point in space to every moment in history, through the unbroken framework of Kamau. In the vast expanse of the universe, the intricate fabric of spacetime weaves together the dimensions of time and space, creating a profound backdrop for the unfolding of cosmic events. The universe might hold additional dimensions that extend beyond the 4 familiar to us. Certain advanced theories in physics propose that the well-known 4 dimensions may not encompass the complete reality. Concepts like string theory suggest that there are extra dimensions concealed from our awareness, as they are tightly compacted and folded at scales beyond our comprehension. The additional dimensions may provide insight into the relative weakness of gravity compared to other fundamental forces, as well as the potential for a unified framework encompassing all the forces of nature. Even though these dimensions remain beyond our direct observation, their influence may manifest in delicate gravitational measurements or in the collisions of high-energy particles. Ongoing experiments seek to uncover indications of these concealed dimensions of existence. Should they ever come to light, the comprehension of the universe will broaden significantly, uncovering that the space we traverse daily might merely represent a fraction of a far more intricate and abundant cosmic structure. Minuscule, concealed dimensions may exist, intricately folded at subatomic scales. In the realm of string theory, it is proposed that there may be extra dimensions present all around us, intricately folded to such an extent that they remain smaller than atoms. The curled-up dimensions would dictate the properties of particles, including mass and charge, based on their shape. Envision a straw seen from a distance. What seems like a straightforward line reveals a complex circular depth upon closer inspection. Extra dimensions might operate in a manner akin to being unseen at human scales, yet they are essential to the very framework of the universe. They existed at the Planck length, the smallest measurable scale, influencing the interactions of particles and the combination of forces. Even though these dimensions remain unseen, physicists are on a quest for indirect evidence through particle accelerators and gravitational experiments. Uncovering them would reshape our perception of reality, revealing that space conceals complex patterns that are smaller and more fundamental than anything previously witnessed. String theory proposes the existence of 10 or 11 dimensions. String theory suggests that the fundamental components of reality consist of minuscule vibrating strings, as opposed to point-like particles. Every vibration is linked to a distinct particle or force. For the mathematics of this theory to hold true, space-time is required to encompass more than 4 dimensions, typically 10 or 11, varying by the specific version. The extra dimensions are believed to be compact and imperceptible at human scales, tightly curled in a manner that eludes direct perception. The hidden dimensions present an opportunity for the theory to bring together all known forces, including gravity, into a single, coherent framework. While experimental confirmation is still out of reach, string theory has offered deep insights into black holes, quantum gravity, and the very fabric of the universe. It implies that the world we can see is merely a fragment of a much larger dimensional reality that is yet to be comprehended. To behold all dimensions would transform the very essence of reality. Their senses are confined to the perception of 3 dimensions of space, leading them to experience the world through surfaces, edges, and volumes. Should we gain the ability to perceive higher dimensions, the world around us would take on a completely new form. What may seem like isolated objects could actually share a connection, and occurrences that look to be in a linear progression might actually happen simultaneously. From a broader viewpoint, the concepts of distance and isolation may begin to fade in significance. Mathematics invites us to envision these realms, where geometry unfolds in ways that surpass our ability to visualize. Certain theories propose that these dimensions play a crucial role in shaping the universe's essential characteristics, affecting everything from the behavior of particles to the structure of the cosmos. Should we have the ability to observe all dimensions, we could grasp entire timelines simultaneously, unveiling connections that currently appear obscured. The exploration of higher dimensions invites a profound reconsideration of existence, hinting that the familiar world we perceive might merely represent a limited fragment of a far more complex and layered reality. The Big Bang brought forth the very fabric of space and time simultaneously. The universe's inception transcended the confines of space. The inception of space can be traced back to the moment of the Big Bang. In that moment, the cosmos unfurled from an intensely hot and compact state, bringing forth both space and time in a singular, magnificent event. In a realm untouched by the passage of time, there existed no prior moment to this event, for the very essence of time had yet to unfold. As the universe expanded, matter and energy began to cool and disperse, ultimately giving rise to stars, galaxies, and planets. The subtle remnants of this occurrence, referred to as the cosmic microwave background, continue to illuminate the sky in the present day. Modern cosmology reveals that space-time is not merely a static container. Rather, it is a dynamic entity that evolves alongside the universe. Inquiring about the events preceding the Big Bang is akin to questioning what exists north of the North Pole. The notion simply loses its relevance. The inception of space-time signifies the genuine starting point of all existence, the initial instant from which every subsequent moment emerges. Before the Big Bang, there existed nothing. The Big Bang was not an event that unfolded in the vastness of space. It marked the very inception of space and time. Prior to its occurrence, there existed no prior moment, for time had yet to commence. The laws of physics, as they are comprehended, falter when examined in relation to that unique instant. Inquiring about what existed prior to the Big Bang resembles questioning what is found north of the North Pole. Such a question holds no significance within the context of our universe. Time commenced as the universe unfolded from a condition of boundless density and temperature into the expansive cosmos we observe today. With each passing second, every atom and every star emerged from that initial revelation. In the beginning, space and time were closely linked, creating the very basis upon which all forms would eventually emerge. The Big Bang signifies not just the inception of matter, but the dawn of existence as a whole. The universe lacks a center, as space is perpetually expanding in all directions. As one gazes into the vastness of the universe, it becomes evident that galaxies seem to drift away from us in all directions. It may appear that Earth occupies the heart of a cosmic explosion. Yet this perception is merely an illusion. The expansion of the universe is not merely an explosion into a void. Rather, it represents the very stretching of space itself. Every point in the cosmos observes the same pattern of recession, as the expansion unfolds uniformly across the entirety of space. The Big Bang did not take place at a specific central location. Rather, the whole universe was initially held within an incredibly dense state that expanded in a uniform manner. Regardless of your position, remote galaxies seem to drift away, and the greater their distance, the swifter their motion becomes. This universal symmetry signifies that the cosmos lacks a favored center. The expansion of space unfolds as a continuous process, shaping the very geometry of reality itself. Galaxies drift apart, while the very fabric of spacetime stretches and unfolds. Galaxies do not traverse through a pre-existing space as if they were remnants of an explosion. Instead, the distance between them is widening. The galaxies themselves remain relatively still, bound by their own gravity, as the fabric of space-time unfolds around them. As it expands, the wavelengths of light moving through it also elongate, resulting in the redshift that astronomers detect in far-off galaxies. This redshift serves as clear proof of the universe's continuous expansion. Over billions of years, this stretching has transported galaxies increasingly farther apart, transforming the once dense early cosmos into the expansive, sparsely populated universe we observe today. Even the light from distant stars is drawn to longer wavelengths as the expanse it traverses continues to expand. The expansion of space-time represents more than mere movement. It signifies a fundamental transformation in the geometry that shapes distances and motion across the universe. Expansion signifies not the movement of objects through space, but rather the very growth of space itself. A prevalent misunderstanding exists regarding the notion that galaxies are racing through the cosmos, distancing themselves from each other. In truth, they remain largely fixed in relation to their surrounding areas, while it is the very fabric of space that is undergoing expansion. To illustrate this, picture dots placed on a balloon. As the balloon expands, the dots drift away from one another, not due to their movement across the surface, but rather because the surface itself expands. Similarly, the universe unfolds, generating additional space among galaxies, all without requiring movement through an external emptiness. This growth knows neither edge nor center. It occurs consistently in every place. As the universe expands, the light traversing its vastness stretches, offering insights into the rate of this expansion. This insight redefines the very essence of motion, uncovering that the expansion of the universe is fundamentally the expansion of space-time, rather than merely the relocation of matter within it. The acceleration of space-time's expansion unfolds before us. For a significant portion of cosmic history, it was widely accepted among scientists that gravity would eventually bring a gradual halt to the universe's expansion. In the late 20th century, astronomers stumbled upon an unexpected revelation. The distant supernovae appeared dimmer than anticipated, suggesting that the expansion was not decelerating, but rather accelerating. The universe expands at an accelerating pace as time unfolds, This acceleration suggests the presence of an enigmatic energy that counteracts gravity, permeating the entirety of space. The revelation reshaped the understanding of the universe, compelling researchers to reconsider the enduring destiny of all things. As space-time continues its relentless expansion, distant galaxies will ultimately drift beyond our observable horizon, disappearing from sight for all eternity. The acceleration indicates that the universe's expansion is not merely a straightforward extension of the Big Bang's initial force, but rather a new chapter influenced by an enigmatic and all-encompassing force. The expansion of space-time continues to unfold, intensifying and transforming the cosmos across the grandest scales imaginable. It is possible that dark energy is the force behind that acceleration. In an effort to elucidate the accelerating expansion of the universe, scientists brought forth the notion of dark energy, an enigmatic force that permeates all of space uniformly. In contrast to gravity's unifying force, dark energy presents a unique phenomenon, exerting a repulsive influence that drives galaxies away from one another. At present, it constitutes roughly 70% of the universe's overall energy content. The true nature of dark energy remains a mystery, possibly linked to the cosmological constant that Einstein once introduced and subsequently rejected. The effects can be assessed by observing supernovae, the cosmic microwave background, and the large-scale structure of galaxies. If dark energy remains constant, the universe will perpetually accelerate, gradually becoming colder and emptier as time unfolds. Grasping the nature of dark energy stands as one of the most formidable challenges in contemporary physics, possessing the potential to unlock the secrets of the ultimate destiny of space-time. The true nature of dark energy remains a mystery to us. The enigma of dark energy stands as one of the most significant puzzles within the realm of science. It represents a significant portion of the universe's energy, yet remains elusive to direct detection and understanding of its true nature. It neither emits light nor interacts with matter, nor does it cluster in the manner of ordinary energy. It merely speeds up the growth of space-time. Certain theories propose that it may be an inherent characteristic of space, a persistent energy density arising from quantum fields. Others propose that it might vary over time, or that our understanding of gravity is incomplete. Despite decades of observation, every measurement confirms only its effect, not its essence. Whatever dark energy is, it determines the long-term evolution of the cosmos. Whether the universe expands forever or meets a different fate depends entirely on this invisible influence that fills the void, yet defines the structure of everything within it. The universe's geometry depends on its density. The overall shape of the universe is determined by how much matter and energy it contains. If the total density is high enough, gravity can curve space-time inward, creating a closed geometry similar to the surface of a sphere. If the density is too low, space-time curves outward, producing an open, saddle-like shape. A perfectly balanced density yields a flat universe, where parallel lines remain parallel forever. Astronomers study the cosmic microwave background radiation to measure this curvature, using subtle patterns in the light to infer the geometry of space-time. So far, the evidence suggests that the universe is very close to flat, with only a tiny margin of error. The relationship between density and curvature reveals how matter, energy, and geometry are inseparably connected. The universe's shape is not imposed from outside, but sculpted from within by its own contents. A flat universe means space-time has perfect balance. A flat universe is one in which the geometry of space-time follows the familiar rules of Euclidean space. Parallel lines never meet. Triangles have angles that add up to 180 degrees, and large-scale curvature is effectively zero. Achieving this balance requires a precise relationship between matter, energy, and expansion rate. If there was slightly more mass, the universe would eventually collapse slightly less, and it would expand too quickly for galaxies to form. The fact that it is so finely balanced puzzles cosmologists who call it the flatness problem. The leading explanation is cosmic inflation, a brief but intense burst of expansion in the early universe that smoothed out any initial curvature. The result is a cosmos that appears geometrically perfect, a delicate equilibrium that continues to define the structure and destiny of everything within it. Curved spacetime could loop back on itself. If spacetime is curved enough, it could wrap around, allowing a traveler moving in one direction to eventually return to their starting point without ever turning around. This concept applies to a closed universe where the geometry of space resembles the surface of a higher dimensional sphere. In such a universe, there would be no boundaries or edges, yet space would be finite. You could, in theory, keep towing straight and eventually arrive where you began, though the scale of such a journey would be unimaginably vast. Observations so far suggest that the universe is nearly flat, but tiny deviations could reveal subtle curvature. If the cosmos does curve back on itself, it would mean that the universe is self-contained, a structure with no outside and no end, where space and time form an endless loop of cosmic continuity. A closed universe might eventually collapse in a big crunch. If the density of matter and energy in the universe were high enough, gravity could eventually overcome the expansion and pull everything back together. In such a scenario, galaxies would slow their outward drift, reverse course, and move closer until the entire cosmos collapsed in a final, fiery contraction. This hypothetical event is known as the Big Crunch. The universe would end as it began, in an extremely dense and hot state. Some theories suggest that such a collapse might be followed by a new expansion, forming a cycle of births and deaths. Although current observations indicate that the expansion is accelerating rather than slowing, the possibility of a closed, recollapsing universe remains a fascinating idea. The Big Crunch reminds us that space-time itself is dynamic, capable of both unfolding and folding back into the singular state from which it first emerged. An open universe could expand forever. If the universe does not contain enough matter and energy to halt its expansion, it will continue to grow indefinitely. In this open universe scenario, galaxies will drift farther apart until the night sky becomes dark and empty. Stars will exhaust their fuel. Black holes will slowly evaporate, and all remaining matter will decay into faint radiation. Over unimaginable timescales, even light will stretch to wavelengths too long to detect, leaving a cold, featureless void. This future, sometimes called the heat death of the universe, represents a state of maximum entropy, where energy is evenly distributed and no work can be done. Although it sounds bleak, this fate is consistent with current observations showing that expansion is accelerating. An open universe expanding forever demonstrates that space-time is not eternal in form, but ever-changing, shaped by the delicate balance of its own contents. The shape of space-time determines the fate of everything. The geometry of the universe is more than an abstract concept. It dictates how everything within it evolves. Whether the cosmos is open, closed, or flat determines whether it will expand forever, collapse, or hover in balance. The shape of space-time affects how light travels, how galaxies form, and even how time unfolds. Small variations in density in the early universe caused local curvatures that became the seeds of stars and clusters. The large-scale curvature influences the global destiny of everything. In this way, geometry becomes destiny. Space and time are not passive backgrounds, but active participants in cosmic evolution. The curvature of space-time, sculpted by matter and energy, is the ultimate architect of the universe's story, from the formation of the first atoms to the possible fates that lie billions of years ahead. Even empty space has structure. At first glance, a perfect vacuum might seem truly empty. Yet modern physics reveals that even regions without matter or radiation possess properties and energy. Space is filled with quantum fields that fluctuate constantly, creating fleeting disturbances that give rise to virtual particles. These fluctuations contribute to a background energy that pervades the universe. They also affect the behavior of matter and light, influencing how particles interact and how forces operate. The so-called vacuum is not void, but a dynamic, restless sea at the foundation of reality. Even the expansion of the universe may be linked to this energy. What appears empty is, in truth, an intricate landscape of potential and activity. Space, far from being nothingness, is a living field whose invisible structure supports and shapes everything that exists within it. Quantum fluctuations stir the vacuum of spacetime. Even in the absence of matter and light, the quantum vacuum seethes with activity. Tiny fluctuations in energy continually occur due to the uncertainty principle, which forbids absolute stillness. These fluctuations briefly create pairs of virtual particles that appear and vanish almost instantly, borrowing energy from the vacuum before returning it. Though they exist for only fractions of a second, their effects are measurable. Their influence subtly modifies the behavior of electrons, adjusts energy levels within atoms, and impacts the dynamics of forces. In the early universe, fluctuations may have sown the initial subtle differences in density that eventually blossomed into galaxies. The vacuum is not devoid of substance. Rather, it teems with quantum activity, creating a foundation that challenges the distinction between being and non-being. At the most profound level, spacetime exists as a dynamic field, where the processes of creation and annihilation unfold ceaselessly and without visibility. In the vastness of the cosmos, one might think of space as devoid of substance, yet it is always filled with unseen potential and hidden wonders. Even in the expansive voids that lie between galaxies, the cosmos holds secrets that go beyond mere appearances. It is imbued with subtle radiation, dusty particles, and shifting quantum fields. The vibrancy of these fields ensures that every corner of the universe is infused with some form of activity. This constant backdrop shapes the actions of particles and determines the evolution of the cosmos. The journey of light through the vastness of intergalactic space encounters these delicate interactions, with gravity reacting to the energy they possess. At the tiniest levels, the vacuum teems with activity on the grandest scale. It contributes to the expansion of the cosmos. What seems like emptiness is, in fact, the most essential state of matter and energy, a foundational resonance from which all physical processes emerge. In reality, the most tranquil corners of the universe are far from silent. They resonate softly with the concealed rhythms of spacetime. Virtual particles appear and disappear in a ceaseless dance of existence. In quantum physics, empty space serves as a stage for an ongoing dance of creation and destruction. In a fleeting dance, virtual particles appear, engage with one another, and then dissipate. Yet they leave behind delicate hints of their existence. Though they remain unseen, their impact is undeniably quantifiable. These transient entities lead to occurrences like the Casimir effect, in which two metal plates in a vacuum feel a discernible force resulting from the pressure of these quantum fluctuations. Virtual particles play a crucial role in elucidating the interactions of real particles, serving as intermediaries for forces such as electromagnetism. Their relentless emergence and vanishing create a haze that obscures the line separating existence from non-existence. In the vast expanse of space, there is no emptiness. Rather, it serves as a vibrant stage where the essence of existence dances at the tiniest scales imaginable. The universe's apparent stability is underpinned by an unseen tempest of creation that perpetually unfolds, a relentless choreography of energy, hidden beneath the serene facade of reality. At the smallest scales, time may indeed be quantized. Just as matter and energy exist in distinct units, it is conceivable that time, too, could have a minimum measurable increment. Some theories of quantum gravity suggest that time does not progress in a smooth manner, but instead moves forward in minuscule, indivisible increments, known as quanta. At scales approaching the Planck time, approximately 10 to the negative 44 seconds, the seamless weave of space-time might fragment into its essential components. If accurate, this suggests that the universe functions according to a cosmic clock governed by a fundamental limit to its resolution. The continuous motion and change would merely be illusions within these remarkably brief intervals. While experimental testing of this idea remains out of reach, it presents a promising avenue for the integration of relativity and quantum mechanics. The idea that time could be composed of discrete units implies that the very essence of reality is formed from individual instances, intricately connected to create the continuum we experience. At the Planck scale, the fabric of spacetime takes on a chaotic and unpredictable nature. At distances smaller than the Planck length, the nature of spacetime becomes increasingly complex and irregular. In a realm where quantum effects reign supreme, geometry transforms into a tumultuous ocean of ceaseless fluctuations. This scale, approximately 10 to the negative 35 meters, signifies the threshold where gravity and quantum mechanics converge. The narrative unfolds with a sense of disarray as the once orderly fabric of space and time dissolves into a tumultuous sea of shifting relationships. Tiny wormholes may open and close, rendering the distinction between here and there utterly meaningless. In the realm known to physicists as quantum foam, intriguing phenomena unfold. It embodies the essence of all being, the realm where the traditional understanding of space-time dissolves. Grasping this regime necessitates a theory of quantum gravity, a pursuit that stands as one of the most significant objectives in the realm of science. At the Planck scale, the universe's calm surface reveals a turbulent foundation, serving as a reminder that beneath every structure there exists a restless storm of creation. The Planck time represents the smallest conceivable unit of time. Physicists define the Planck time as the smallest meaningful interval that can exist, approximately 10 to the power of negative 44 seconds. Below this threshold, the established principles of physics cease to function, and the notion of time itself becomes devoid of significance. It signifies the time required for light to traverse a single Planck length, the tiniest conceivable unit of distance. At scales shorter than this, quantum uncertainty takes precedence over space-time, rendering measurement unfeasible. The Planck time represents the ultimate boundary of physics, the point at which our comprehension ceases. In the primordial dawn of the universe, time might have adhered to these constraints, advancing in distinct intervals rather than gliding seamlessly. Though unimaginably brief, this unit encapsulates the smallest heartbeat of reality, the quantum pulse from which the continuous rhythm of the cosmos ultimately emerges. The Planck length establishes the boundary of physical significance. The Planck length, approximately 10 to the power of negative 35 meters, signifies the tiniest distance where the established laws of physics are applicable. At this scale, the gravitational effects of quantum mechanics intensify to the point where the very fabric of space loses its clear definition. Efforts to gauge or witness anything on a smaller scale would demand energies of such magnitude that the area under examination would inevitably succumb to the formation of a black hole. The Planck length emerges as more than a mere figure. It stands as a threshold that distinguishes the realms of the describable from the undefined. It signifies the realm in which quantum mechanics and general relativity are destined to converge into a unified theory of quantum gravity. This minuscule distance lies far beyond the grasp of any experiment, yet it establishes the ultimate resolution of the universe, the tiniest pixel of reality, where geometry, energy, and probability intertwine in a delicate dance. Extended, distinct ideas yet unified, quantum gravity endeavors to bring together the minuscule and the immense. The behavior of the smallest particles is described by quantum mechanics, whereas the vast structures of space, time, and gravity are governed by general relativity. Every theory operates elegantly within its specific realm, Yet they remain unwilling to collaborate at the farthest edges of nature. Quantum gravity represents the endeavor to unify these concepts, forming a cohesive framework that elucidates phenomena ranging from subatomic particles to galaxies. In the vicinity of black holes or at the dawn of the universe, the two sets of laws are required to function in unison. Yet their equations presently stand in opposition to one another. Researchers delve into a multitude of potential avenues, such as string theory, loop quantum gravity, and models of emergent spacetime. Each implies a profound connection between geometry and matter, hinting at a potential interchangeability between the two. Success would unveil the essential fabric of reality and elucidate the behavior of the universe at its most extreme boundaries. Quantum gravity serves as the connection between the minuscule and the incomprehensibly expansive. The principles of general relativity and quantum mechanics continue to stand at odds with one another. Einstein's theory of general relativity presents space-time as a smooth and continuous fabric, whereas quantum mechanics asserts that energy and matter exist in distinct, probabilistic units. The merging of these perspectives creates contradictions that challenge reason. Calculations regarding the interior of black holes, or the initial moments of the Big Bang, produce infinities that cannot physically exist. This conflict represents one of the most profound enigmas in the realm of science. It is understood by physicists that both theories hold true within their respective realms, yet each falters when extended into the domain of the other. The universe is bound by a singular set of principles, yet the equation that harmonizes them remains elusive. Investigations into high-energy particles, gravitational waves, and the thermodynamics of black holes could reveal significant insights. Resolving this tension would transform the field of physics, uncovering a unified portrayal of nature that encompasses everything from the quantum foam to the formation of galaxies and beyond. It is possible that space-time emerges rather than being a fundamental aspect of reality. Some scientists propose that space-time may not be the fundamental essence of reality, but rather a construct that emerges from more fundamental principles. From this perspective, space and time emerge not as fundamental components of the universe, but as outcomes of more profound quantum phenomena. Just as temperature arises from the movement of countless atoms, so too could space-time arise from the connections between quantum states or particles. If accurate, the geometry we perceive might be a grand illusion, intricately woven from a foundation of information and entanglement. At the tiniest scales, continuous space may not exist. Instead, there are only discrete interactions that create our perception of distance and duration. This idea transforms the entire landscape of physics comprehension. It implies that reality is constructed not from voids, but from the unseen ties that form its essence. A tapestry of the universe, intricately crafted from the very essence of connection. Entanglement might serve as the intricate thread that binds the fabric of space-time. Quantum entanglement stands out as one of the most peculiar phenomena in the realm of physics. As two particles become entangled, they forge a connection so deep that the act of measuring one immediately influences the other, regardless of the distance separating them. Some physicists now believe that this connection could constitute the fundamental essence of space-time itself. In this image, the essence of space unfolds from the intricate web of interconnected particles, where geometry illustrates the intensity and arrangement of their connections. As the system grows increasingly intertwined, a sense of continuity and connection within space emerges more prominently. Should the entanglement be severed, the very fabric of space-time could unravel or face complete collapse. This concept presents a route to harmonizing quantum theory with gravity, transforming the notion of space from a mere backdrop into a realm that emerges from information. The cosmos unfolds as a vast web of entanglement, where each thread intricately weaves together the very structure of all that exists. Some theorists propose that the fabric of space is constructed from quantum information. Contemporary physics increasingly suggests that information serves as the fundamental basis of reality. In certain theories, each point in space is linked to a minuscule unit of data that encapsulates the quantum state of the universe. The informational bits engage with one another, exchanging energy and collectively forming what we recognize as geometry and motion. Evidence for this emerges from black holes, which seem to retain their contents, not within their volume, but rather on their surface area. The information contained within those areas increases proportionally, suggesting that space itself could be quantized in analogous manners. Should the universe be composed of information, it follows that physics becomes a process of computation, with each particle interaction representing a form of calculation. The structure of that ongoing computation would be space, a holographic lattice of relationships that encodes everything perceived, felt, and measured within the immense machinery of the cosmos. The passage of time might emerge from the expansion of entanglement. Time may not simply serve as a backdrop for events to occur. Rather, it emerges as a property arising from the deepening connections at the quantum level. As systems interact, they become increasingly intertwined, creating a network of connections that deepens in complexity as time progresses. This increase in entanglement may shape the very course of time. The universe transforms from simpler forms into more intricate connections, creating a directionality of time that flows from the past into the future. In this regard, time does not serve as a fundamental dimension. Rather, it mirrors the transformations within the informational framework of the universe. As particles share their secrets, the very essence of space-time transforms alongside them. Clocks do not quantify an already existing flow. Rather, they indicate the pace at which systems create connections. The passage of time unfolds as a narrative crafted by the universe, intricately weaving its own fabric through entanglement, forming a tapestry of history from the essence of quantum connection. The progression of time moves from structure to chaos. The passage of time unfolds with a distinct trajectory that we perceive in every instant, while the fundamental principles of physics remain indifferent to any particular direction. The perception of time's forward movement stems from entropy, which serves as a measure of disorder. In closed systems, entropy is destined to rise, illustrating the universe's journey from states of greater order to those of lesser order. Shattered glass remains in disarray, and warmth does not transfer from a cooler body to a warmer one without effort. In the early universe, a remarkable order prevailed, granting time a clear direction as entropy began its ascent. This gradual increase leads to the emergence of memory, causality, and change. In its absence, every event would appear to be reversible, causing the distinction between past and future to dissolve. Entropy transcends being just a statistical property. It serves as the cosmic engine that imparts a one-way current to time, transforming symmetry into history and stillness into motion. Time finds its direction through entropy. Entropy illustrates the various configurations a system can adopt while preserving its overall appearance. As entropy rises, a multitude of configurations emerges, leading systems to gravitate instinctively towards disorder. This process reveals the reasons behind the perception of time's forward movement. Reversing it would necessitate that every particle retrace its path with precision, an occurrence so unlikely that it would never happen in reality. The rise of entropy is the foundation for phenomena ranging from the melting of ice to the vast evolution of galaxies. The universe commenced in a remarkably low state of disorder, and its gradual increase has fostered the perception of continuity and advancement we refer to as time. Every irreversible process we witness, whether it be the combustion of stars or the rhythmic pulse of a human heart, reveals a profound resonance. The passage of time is shaped by the intricate mathematics of probability, woven into every action of matter and energy. If entropy were to decrease, one might imagine time flowing in reverse. If entropy were to universally decrease, the line separating past from future would dissolve entirely. Events would unfold in a manner that revealed a transformation. where disorder gradually yielded to harmony, and fractured systems found a way to mend themselves effortlessly. In principle, physics permits this, yet in practice, it remains highly improbable due to statistical unlikelihood. The multitude of ways in which particles can arrange themselves into chaos vastly surpasses the limited configurations that lead to order. A universe characterized by diminishing entropy would obliterate memory and the concept of causality, as effects would occur prior to their causes rather than following them. This unexpected turn confronts our fundamental beliefs regarding the nature of time and being. While it is possible for entropy to decrease in specific instances, such as the emergence of life or the creation of stars, these phenomena invariably result in an increase in disorder in other areas. The progression of time is thus upheld by the continual increase of entropy, grounding each instant in the unchangeable development of the universe's narrative. In the early universe, a remarkable sense of order prevailed, starkly contrasting with the chaos observed in the present day. In the moments following the Big Bang, the universe presented itself as a smooth, uniform, and dense expanse. In the midst of what seemed like chaos, there existed a state of remarkably low entropy, indicating a level of order that surpassed the structured cosmos of today. There existed a limited number of configurations for matter and energy to inhabit. Over billions of years, as the universe expanded and cooled, tiny fluctuations transformed into stars, galaxies, and planets, significantly enhancing entropy. This ascent characterizes the progression of time. The initial straightforwardness paved the way for intricate formations to arise as disorder increased, resulting in life, evolution, and transformation. The origins of the universe remain a mystery, as scientists have yet to grasp why it commenced in such an unexpectedly organized manner. The answer may uncover the reasons behind the very direction of time itself. The evolution of the universe, shifting from smoothness to complexity, represents not decay, but a profound transformation. It embodies a continuous balancing act between order and chaos, propelling the narrative of cosmic history forward. With each passing second, the entropy of the universe continues to rise. The steady growth of entropy weaves through the universe, defining the direction of time. Each process that transforms energy from one form to another plays a role in this growth. The stars, in their majestic dance, fuse hydrogen into helium, casting warmth into the vastness of the cosmos. Black holes devour both matter and light, contributing to their vast entropy. Living organisms engage in the process of metabolizing energy, which results in the creation of local order and the release of waste heat. Every one of these actions signifies a minor progression in the overarching ascent of chaos. Over billions of years, the increase in entropy has led to a cosmos that is now predominantly cold and diffuse, with energy dispersed widely across expansive stretches. Nevertheless, this continuous journey also ignites imagination and intricacy. The transition of energy from order to disorder creates a fleeting space where systems such as planets and life can momentarily thrive. With each passing second, the imprint of entropy deepens, capturing the irreversible rhythm of the universe's unfolding narrative. Time flows in a unique manner in the presence of massive objects. Gravity distorts not just the fabric of space, but also the passage of time. In the vicinity of a colossal mass, the passage of time is noticeably slower compared to areas where gravitational forces are less intense. This phenomenon, known as gravitational time dilation, has been validated through experiments that compare atomic clocks situated on Earth with those in orbit. The proximity of a clock to a planet or star results in a greater distortion of space-time, thereby elongating the passage of time itself. In the vicinity of a black hole, the phenomenon intensifies, transforming mere seconds into what feels like centuries for those observing from afar. The principle is intricately integrated into technologies such as GPS, which must consider these relativistic differences to operate with precision. The unfolding narrative illustrates that the universe's rhythm is not fixed, but rather flexible, molded by the unseen influence of gravity. Mass and time are intertwined companions, each influencing the other, crafting a universe where every heartbeat, every orbit, and every light beam reveals itself within a tapestry of curved geometry. In the vicinity of a black hole, moments can expand infinitely. As matter nears the event horizon of a black hole, the curvature of space-time intensifies to such a degree that time appears to nearly halt for an observer far away. To that observer, the falling object seems to come to a standstill, gradually diminishing as its light shifts into the realm of invisibility. Yet for the object itself, time flows in its usual manner. It traverses the horizon within a limited span, oblivious to the profound distortions that have taken hold of the external world. This paradox reveals the fluid nature of time and the profound influence of gravity in shaping its course. The area surrounding a black hole's horizon serves as a stage where the fabric of space-time governs all events, transforming moments into infinities and movement into tranquility. What appears everlasting from a distance is, in a different perspective, a fleeting descent. The division between these viewpoints reveals one of the most enchanting enigmas in the realm of physics. At the brink of a black hole, even light finds it challenging to break free. The edge of a black hole, referred to as the event horizon, signifies the ultimate gravitational boundary. From this vantage point, the force of gravity perfectly matches the outward velocity of light. Approaching any nearer, even photons find themselves unable to escape. As light attempts to break free from this area, it diminishes in energy, elongating into longer wavelengths that ultimately dissolve into obscurity. This phenomenon, known as gravitational redshift, illustrates that light adheres to the contours of space-time. By observing the way radiation bends and slows in the vicinity of black holes, astronomers are able to rigorously test the predictions of general relativity with remarkable accuracy. The battle of light, to break free from profound depths, illustrates the undeniable connection between space and gravity. Black holes do not ensnare light merely through force. Rather, they manipulate the geometry of the universe itself, bending the very fabric of reality so that every trajectory ultimately spirals back to the hidden core. To a distant observer, an object descending appears to halt in time. As an object descends toward a black hole, it seems to decelerate and diminish in brightness as it approaches the event horizon. From a distance, the unfolding of events appears to drag on endlessly, as if time itself has expanded each moment into eternity. The object's light fades to a deeper red, diminishing gradually until it disappears entirely. To the object in descent, all sensations remain ordinary. It crosses the horizon and moves deeper, oblivious to anything remarkable. This distinction emerges from the varying behaviors of time and space for observers situated in different gravitational fields. The immense curvature of the black hole causes their perspectives to diverge completely. The distant frozen image is not an illusion, but a genuine representation of the geometry of space-time. It illustrates that time is influenced by gravity, motion, and position, revealing its relative nature. In the vicinity of a black hole, the passage of time transforms into a question of viewpoint and proximity. Unbeknownst to the object, it traverses the horizon, oblivious to its journey. From the perspective of an object descending into a black hole, the event horizon appears not as a barrier or wall, but rather as a commonplace area within the fabric of space-time. The traveler experiences neither a jolt nor a shift as they make their way across it. In the local realm, the study of physics proceeds in its customary manner. However, when viewed from an outside vantage point, the event appears to be eternally suspended just above the horizon. This paradox reveals the intricate ways in which gravity distorts not just the fabric of space and time, but also the very nature of perception. Within the horizon, every conceivable path converges inward toward the singularity, a moment where the laws of physics, as we understand them, cease to apply. For the falling object, the crossing is both unavoidable and ordinary. Yet, for someone watching from the outside, it remains an event that never truly unfolds. Both perspectives hold their own validity within the context they provide. This striking difference illustrates that reality in general relativity is contingent upon one's position and the extent to which gravity influences the flow of time. The perception of space and time varies from one observer to another. Einstein's theory of relativity reveals that space and time are not fixed entities. Two observers, each traveling at distinct velocities or situated in varying gravitational fields, will perceive differing intervals of time and distance between identical events. What one perceives as simultaneous, another might interpret as sequential. The relativity of perception emerges as space-time itself adapts to maintain the unchanging speed of light. Time stretches and contracts, weaving a delicate equilibrium throughout the universe. In the hustle of daily existence, these effects remain concealed. Yet under the influence of high speeds or intense gravity, they reveal their true significance. This principle transforms our comprehension of motion, causality, and the very essence of existence. In the vast expanse of the universe, no singular timeline weaves its way through the myriad of personal journeys that intersect and diverge in intricate patterns. Reality is not confined to a singular perspective. Rather, it is woven from the intersecting viewpoints of everyone navigating the fabric of spacetime. Simultaneity exists only as a mirage. For one observer, events may unfold simultaneously, while for another, in motion relative to them, those same events might take place at different intervals. This phenomenon, referred to as the relativity of simultaneity, arises directly from the unchanging nature of the speed of light. As light consistently travels at a uniform speed, those observing from different frames of reference must recalibrate their measurements of time and space to maintain coherence. This indicates that a universal present is not collectively experienced throughout the cosmos. Each observer holds a unique perspective of reality, shaped by their movement and location. What seems to be in harmony in one moment can reveal itself in a series of events in another. This concept questions the common belief in the absoluteness of time, yet it has been consistently validated through experimentation and observation. The universe does not move in harmony, but resonates with myriad intertwining rhythms, each connected to the distinct journey of its observer through the fabric of spacetime. Two events that appear to be in sync for one person may not hold the same significance for another. Picture yourself on a train platform as two flashes of light illuminate the front and back of a passing train. To them, the flashes appear to occur at the same time. For a passenger within the train, the events unfold at different moments due to the train's movement, altering the way light arrives to them. Each observation holds validity when considered from its respective perspective. This example encapsulates the core of relativity, challenging the notion of a singular, universal time. The notion of simultaneity is contingent upon the observer's motion, illustrating that time is intricately interlaced with space, inseparable from it. The relativity of experience fosters a sense of harmony rather than contradiction. It guarantees that all observers reach a consensus on the physical laws, regardless of their differing perceptions of the timing of events. The fabric of time and space seamlessly adjusts, maintaining the coherence of the universe's geometry. Clocks in motion tick at a different pace compared to those that remain still. It was revealed by Einstein that the passage of time is not uniform for all individuals. As an object accelerates to high speeds, the passage of time for it appears to decelerate when compared to an object that remains stationary. This peculiar phenomenon, referred to as time dilation, has been validated through various methods. Subatomic particles that are expected to decay in mere moments manage to endure for a significantly longer duration when they move at speeds approaching that of light. Atomic clocks on airplanes or satellites operate at a slightly slower pace compared to their identical counterparts on the surface of the Earth. None of this is a mere illusion. the universe upholds the consistency of physical laws in a remarkable manner. All observers, whether in motion or at rest, perceive the speed of light as constant. For that to happen, time itself must undergo a transformation. The quicker an object travels, the more sluggish its seconds become. This serene unfolding of time maintains the harmony of the cosmos, intertwining motion, light, and experience within a singular, graceful geometry. As the rulers move, they appear to shrink along the path of their motion. As time decelerates for objects in motion, so too does space adapt. A ruler or spacecraft moving at high speed will seem to shrink in length along the direction of its travel when observed by someone who is stationary. This phenomenon, referred to as length contraction, naturally accompanies time dilation. The phenomenon occurs due to the unwavering constancy of light's speed for every observer, regardless of their motion. In order to maintain that unwavering nature, both space and time must evolve in unison. The object remains unchanged within its own frame of reference. All seems to be as it should be. Yet, from the perspective of an external viewer, distances seem to shrink while moments elongate, guaranteeing that the principles of physics remain in harmony. Repeated confirmations have emerged from experiments utilizing high-energy particles. As they navigate through accelerators, their trajectories and durations unfold precisely in accordance with the predictions of relativity. The interplay of space and time weaves together seamlessly, upholding the equilibrium that forms the foundation of the universe. As time stretches, space contracts in a fascinating interplay. Relativity brings together space and time into one cohesive framework, bending and shifting in harmony whenever motion takes place. As an object accelerates, the passage of time for it diminishes, and its length contracts in the direction it moves. The effects maintain the unwavering speed of light and guarantee that the laws of physics are consistent for every observer. The relationship between the expansion of time and the compression of space illustrates that neither element can stand alone. These represent points within a profound structure that shapes the very essence of existence. For astronauts journeying close to the speed of light, the universe before them would appear to be compressed, whereas those on Earth would observe the travelers' clocks moving at a slower pace. Every observer inhabits a stable reality, yet their observations vary in ways that perfectly reflect each other. The equilibrium of space and time serves to maintain the coherence of the universe, transforming relativity from a paradox into a state of perfect harmony. In unison, they maintain the unwavering constancy of light's speed. No experiment has ever discovered light traveling at any speed other than its universal value in a vacuum. No matter if the source approaches or recedes, whether you are in motion alongside it or remaining stationary, the outcome remains the same. This unwavering nature may appear unfeasible unless the very fabric of space and time bends to maintain it. That is precisely what relativity illustrates. As clocks move more slowly and distances appear to shorten, these phenomena work together to guarantee that the speed of light is consistently measured as constant. This unwavering consistency ensures that the equations governing nature remain valid for all, irrespective of their state of motion. It further positions light as the supreme envoy of the cosmos, delineating the boundaries of interaction and consequence. Each photon journeys through a framework that adapts to preserve balance, serving as a reminder that even the most basic constants conceal a deep interconnectedness among distance, time, and the geometry of existence. Truth. Space-time diagrams serve to illustrate this interconnectedness. In the quest to grasp the intricate relationship between space and time, physicists turn to the insightful tool of space-time diagrams. These diagrams illustrate position along one axis and time along another, transforming abstract equations into a visual representation. Each object traverses a world line, a trajectory that reveals its existence in both time and space. An unmoving object descends along a vertical path through time, whereas a swiftly moving one leans toward the horizontal, illustrating the intricate interplay between motion, space, and time. The trajectory of light's world line establishes the maximum speed permissible for all forms of motion. In this depiction, the concepts of time dilation and length contraction emerge effortlessly as straightforward geometric connections. The diagram serves to illustrate the relationships between events, highlighting how some can impact others, while certain occurrences remain entirely separate. Space-time diagrams reshape our understanding of relativity, illustrating that each life, every signal, and every journey intertwines as a thread in the same four-dimensional tapestry that characterizes the essence of the universe's conclusion. Light cones illustrate the relationships between events and their potential influences on one another. Within the intricate weave of space-time, each event radiates potential trajectories for light, dispersing in every direction. These paths create a structure known as a light cone, representing the area of space and time that can be influenced or accessed by that particular event. The interior of the cone symbolizes all that lies within its reach, whereas the exterior delineates what will eternally remain out of grasp. Light cones establish the framework of causality, outlining the relationships between events and their potential influences on one another. As time unfolds, they stretch further, broadening the realm of potential impact. Yet they remain confined by the immutable boundary established by the speed of light. The structure of these cones illustrates the necessity of cause preceding effect and highlights how faster-than-light travel could fundamentally alter the fabric of reality. Each action, whether a flicker or a stellar explosion, exists within its unique realm, weaving the intricate tapestry of connections that provide form and harmony to the universe. Within the confines of your light cone resides all that has the potential to influence you. From the moment of birth, every photon, sound wave, or particle that has ever come into contact has journeyed within the confines of your light cone. This unseen realm delineates your individual segment of the cosmos, encompassing all occurrences that might affect you and all potential future events you could eventually encounter. All that exists beyond it remains eternally out of your reach. The form of this cone broadens with every fleeting second, yet its confines remain rigid, governed by the unchanging velocity of light. No matter how far one travels through galaxies, there are certain distant points in space and times in the future that remain forever out of reach. Within this geometric enclosure, the entirety of one's life unfolds. It links you to all that you have ever witnessed or experienced, while also serving as a reminder that much of the universe remains eternally beyond the limits of your potential encounters. Beyond the confines of the present, everything remains eternally unattainable. The immense expanse of the cosmos will eternally lie beyond the reach of your light cone. Regardless of the duration of your wait or the distance you cover, its signals will forever remain out of reach. This constraint emerges not due to technological shortcomings, but rather from the intrinsic characteristics of space-time itself. The finite speed of light establishes the ultimate reach of influence. Galaxies that are sufficiently distant move away at speeds exceeding that of light because of cosmic expansion, rendering them forever unreachable for communication. Their light remains elusive, their tails eternally shrouded in mystery. The geometry of space-time creates a definitive horizon for each observer, shaping a unique universe constrained by time and distance. It is a reflective notion that isolation is woven into the fabric of existence, yet it simultaneously enriches the significance of connection. In that accessible realm, each beam of light and every fleeting moment holds profound significance, connecting the limited with the boundless through the essence of geometry. The relationship between cause and effect is intricately linked to the structure of space-time. The principle that cause must come before effect is not just a matter of philosophy. It arises from the foundations of geometry. The framework of space-time, characterized by its light cones and curvature, establishes an inherent sequence of occurrences, Nothing can venture beyond its designated path without breaching the universal speed limit, ensuring that no cause can affect an event prior to its occurrence. As massive objects warp the fabric of spacetime, the cones shift and bend, altering the course of time and the trajectories of light. Even in the distorted areas surrounding black holes, the principle holds true. This geometric enforcement guarantees that reality stays consistent and foreseeable. In the absence of it, events might unfold in a chaotic manner, leading to a universe devoid of its logical framework. The essence of causality quietly underpins every experience, shaped not by human thought, but by the intrinsic nature of spacetime, which maintains a consistent structure throughout the universe. Wormholes have the potential to warp that geometry in remarkable manners. The equations of general relativity allow for solutions where spacetime bends in on itself, forming tunnels that link far-off areas. These theoretical structures are referred to as wormholes. Essentially, a wormhole serves as a shortcut through the universe's fabric, enabling a traveler to traverse between two distant points without navigating the space that lies between them. Though they remain unseen, the validity of their mathematics implies that their existence is plausible given the appropriate circumstances. Some wormholes would collapse instantly, while others might remain stable if held open by negative energy, a peculiar form of matter with unusual gravitational properties. Should such structures be found, they might transform our comprehension of distance and connection. It is revealed that spacetime transcends the role of a mere backdrop, emerging as a dynamic and adaptable entity that can manifest remarkable configurations, prompting a re-evaluation of our fundamental beliefs regarding separation and motion throughout the universe. A wormhole connects two far-flung areas of spacetime. Picture a sheet of paper with two distant dots sketched upon it, and then envision folding the paper until those dots meet. A wormhole serves as the spacetime counterpart to that fold, connecting far-off locations within a singular, unbroken framework. In theory, a traveler could approach a wormhole close to Earth and, in an instant, find themselves near a distant star, or even in another galaxy. In the realm of mathematics, general relativity permits such connections. However, maintaining them would necessitate the existence of exotic matter with characteristics that have yet to be observed. At microscopic scales, wormholes may emerge and disappear within the quantum foam of the universe. Some, when sufficiently grand, might act as celestial connections. Though currently speculative, their research broadens our comprehension of relativity, geometry, and energy. Wormholes unveil the notion that space is not a fixed entity, but rather a flexible one, able to form arrangements that unite far-flung areas into a singular, uninterrupted expanse of cosmic potential. The equations proposed by Einstein permit such possibilities in theory. As one delves into the depths of Einstein's field equations, a fascinating array of solutions emerges, depicting wormholes, time loops, and intricate pathways that link distant regions of spacetime. These are not mere fabrications of science fiction. They are authentic mathematical outcomes that emerge organically from the principles of general relativity. The question of whether nature truly constructs them remains unanswered. The necessary conditions could be quite severe, featuring gravitational fields of remarkable intensity and energy densities so unusual that they challenge our existing comprehension of physics. Yet their mere possibility showcases the adaptability of spacetime and the profoundness of Einstein's understanding. Through the translation of gravity into geometry, his equations allow for the existence of universes that are far more peculiar than the one we currently perceive. Wormholes, should they exist, would not violate the laws of physics. Rather, they would embody them in their entirety, revealing that the universe can take on forms and routes that transcend the boundaries of typical understanding. A traversable wormhole might require exotic matter. A wormhole stable enough to pass through would collapse instantly under its own gravity, unless something held it open. Theoretical models suggest that this support could come from exotic matter, a substance with negative energy density. Such material would behave in ways completely opposite to ordinary matter, repelling rather than attracting through gravity. Negative energy does appear in certain quantum phenomena, such as the Casimir effect, but only in minute quantities. To hold a wormhole open, one would need enough of it to counteract immense gravitational pressures. Although the idea remains speculative, it demonstrates how relativity and quantum mechanics intersect. The study of exotic matter pushes physicists toward a unified understanding of both realms. If traversable wormholes ever prove real, they will reveal not only new routes through space, but profound connections between gravity, quantum fields, and the deep structure of space-time. Negative energy could hold a wormhole open. Ordinary matter cannot prevent a wormhole from collapsing, but negative energy might. In quantum theory, negative energy occurs in certain situations where the vacuum behaves unusually, such as between two closely spaced metal plates in the Casimir effect. This type of energy exerts a repulsive gravitational influence, the opposite of what we experience in daily life. If enough could be produced and controlled, it might keep the throat of the wormhole stable, allowing safe passage. Although no experiment has achieved this, the concept links quantum mechanics and general relativity in remarkable ways. It shows that the smallest scales of reality could influence the largest, with quantum fluctuations determining the fate of cosmic structures, whether or not such a feat is ever realized. The idea of negative energy reminds us that space-time remains full of undiscovered possibilities and strange hidden forces. We have never observed one yet. Despite decades of searching, astronomers have found no direct evidence of wormholes. No unusual gravitational signatures, light distortions, or repeating signals indicate that such tunnels exist. That absence, however, does not disprove them. Wormholes, if real, could be rare, unstable, or hidden behind horizons. Detecting one would require immense precision and perhaps new technology capable of identifying their subtle effects on nearby light and matter. Even without proof, scientists study them because they stretch the boundaries of known physics, offering insights into gravity, geometry, and energy. They also serve as valuable thought experiments that help test the limits of Einstein's equations. The mystery endures, fueling imagination and research alike. Whether wormholes remain theoretical or someday become observable, their existence in mathematics shows how deeply the structure of space-time can surprise us with its beauty and complexity. Time travel might be possible through certain wormholes. Some solutions to Einstein's equations suggest that wormholes could connect not just distant points in space, but different moments in time. If one mouth of a wormhole experienced time more slowly than the other, perhaps through motion or gravity, traveling through it might allow a return to the past or a leap into the future. Such possibilities raise profound questions about causality and paradox. Could you visit your earlier self, or change an event that has already happened? Most physicists believe nature would prevent such violations, but the mathematics itself does not forbid them completely. Exploring these ideas helps scientists probe the limits of general relativity and the nature of time itself. Whether practical or not, wormholes remain a theoretical bridge between the familiar flow of time and the deeper, more flexible geometry that underlies the universe. But paradoxes make it complicated. The notion of time travel immediately confronts the problem of contradiction. If you could journey to the past, could you prevent your own existence? Such logical puzzles, known as paradoxes, challenge the consistency of causality. Physicists have proposed many resolutions. Some suggest that the universe forbids paradoxes through a principle of self-consistency, ensuring that any trip to the past simply fulfills history rather than changing it. Others argue that time travel might lead to branching timelines or parallel realities. However, without experimental evidence, these remain ideas rather than realities. The mathematics of general relativity permits closed time-like curves, pathways that loop through time. But quantum mechanics may prevent them from forming. In this tension lies one of physics' greatest mysteries. Whether time's flow is absolute, or whether the universe, through its geometry, can bend that flow into strange and self-consistent shapes. Closed time-like curves could allow loops in time. In certain solutions to Einstein's equations, space-time can curl back upon itself, creating what physicists call closed time-like curves. These are paths that return to their own starting points in time, allowing an object to revisit its past. Such configurations arise in theoretical models involving rotating universes or wormholes, though none have been observed in nature. If they existed, they would challenge our understanding of causality and the sequence of events. Yet the equations themselves do not forbid them, showing that relativity allows more flexibility than intuition suggests. Many scientists believe quantum effects or cosmic censorship prevent such loops from forming, preserving order in the universe. Still, the idea fascinates researchers because it reveals how time, under extreme conditions, could behave like a spatial dimension, folding and connecting, in ways that blur the boundary between past and future. The universe may protect itself from paradoxes through chronology protection. Stephen Hawking proposed that the laws of physics contain a safeguard called chronology protection, preventing time loops that would lead to paradoxes. In this view, any attempt to create a closed time-like curve would trigger quantum effects that destroy the configuration before it could form. Energy levels might rise to infinity, tearing the space-time apart, or sealing the wormhole that would permit backward travel. This principle preserves causality and keeps history consistent. While unproven, chronology protection fits the broader pattern of nature, maintaining coherence even in its most extreme conditions. It suggests that the universe contains built-in defenses against contradictions, ensuring that the sequence of cause and effect remains intact. Time then may be more resilient than it appears, flowing in one direction, no matter how deeply we probe the strange geometries that relativity and quantum theory allow. The flow of time could be an illusion of consciousness. Some physicists and philosophers propose that all moments exist at once within a four-dimensional block universe. In that view, the past, present, and future are parts of a single space-time whole, and what we feel as flow is a feature of how minds process change. Relativity supports this picture by denying any universal now. Different observers slice space-time into nows differently, yet the underlying events remain fixed in the geometry. Neuroscience adds a complementary insight. The brain integrates sensory inputs over a small window of a few tenths of a second, building a unified scene that feels continuous. Memory stitches earlier scenes to the current one, and prediction fills in what comes next, creating the sensation of movement and passage. Entropy still provides a physical arrow that orders events, but the sense of flowing from one moment to another may be a construct. In this interpretation, causality is preserved, since causes and effects are embedded in the block, while consciousness paints the experience of becoming. Time may not move at all. Instead, we move through a landscape of moments, and awareness lights one ridge at a time. Some theories say all moments exist simultaneously. In the block universe interpretation of space-time, the entire history of the cosmos exists at once as a four-dimensional whole. Every moment, from the birth of the universe to its distant future, is embedded within that structure. The passage of time is not something the universe itself experiences, but something perceived by conscious beings moving through the continuum. This view arises naturally from relativity, which shows that simultaneity is relative. Different observers moving at different speeds disagree on what counts as now, suggesting that past, present, and future are not universally distinct. If this interpretation is correct, the flow of time is an illusion created by perception. All events are fixed within the geometry. like pages in a completed book. What changes is the page we happen to be reading, not the story itself, which is already complete from beginning to end. In that view, time does not pass. We simply move through it. According to this perspective, each instant in time is as real as any other. The sensation of time passing emerges from our consciousness, tracing a path through space-time, like a beam of light sweeping across a landscape. Physics describes the world as a four-dimensional arrangement of events, rather than a sequence that unfolds. We do not watch the future become the present and then the past. Instead, we occupy one position in the continuum after another. Our memories record earlier slices, and our expectations project later ones, creating the illusion of motion through something static. Just as we can move through space, our existence moves through time, revealing new views as it goes. This idea challenges everyday experience, but fits perfectly with relativity's geometry, where change is relative, and the universe's structure holds every moment already within it. Space-time could be like a four-dimensional block already complete. Imagine the universe not as something that grows or changes, but as a single, timeless entity containing all events. In this conception, space-time forms a block encompassing every location and every instant. Births, deaths, and cosmic epochs coexist in the same vast structure, each eternally present within its coordinates. The block does not evolve because evolution implies an external time, and none exists beyond space-time itself. What we call the flow of time is our experience of moving along our world line within that fixed geometry. This model explains why physical laws appear deterministic and consistent across all frames of reference. It also dissolves the question of why time moves forward since the block has no movement at all. Instead, our awareness sweeps through its interior, lighting up one region after another, as though flipping through the frames of an infinite film already shot. The past, present, and future may all coexist. In the most literal interpretation of relativity, all points in time are equally real. The past does not vanish, and the future is not yet to be created. Both exist alongside the present in the four-dimensional structure of the universe. The distinction we make between them arises from entropy and perception. Our memories anchor us to earlier states of lower entropy, giving us the impression of progression. Yet nothing in the equations of physics demands that time must flow from one direction to another. Instead, the unfolding of events is part of a static geometric whole. Every cause, every consequence, and every outcome already occupies its place within space-time's lattice. From our limited viewpoint, we experience the universe as a sequence. But in the broader sense, existence may be a single, timeless sculpture, with every era and possibility carved permanently within it. Your perception of the present could be seen as a segment of that larger whole. The present moment may merely represent a slender slice of space-time, a fleeting instance where our consciousness resides. Picture a loaf of bread being sliced, with each piece symbolizing a distinct moment in time. In each moment, we navigate through a singular slice of existence, where our memories weave connections to the past and our hopes reach out toward the future. Physics presents no favored moment in time. What is present for one observer might be seen as the past or future for another. The experience of a dynamic present arises from the workings of the mind, rather than from the fabric of space-time itself. The perception of continuity arises from our biology, yet the universe might be unchanging, with every moment already established. The world line of each observer weaves a continuous thread through the loaf, intersecting with countless other threads, all equally real and coexisting within the eternal geometry that forms the foundation of reality. If that is the case, then every event is intricately woven into the very essence of existence. Should the universe indeed operate as a four-dimensional block, then every occurrence, spanning from the birth of galaxies to your forthcoming thought, is inscribed within its framework. The future remains a mystery, yet it is already woven into the fabric of our world line, poised for discovery. This interpretation suggests a profound sense of inevitability. The laws of physics determine the form of the block, and within that form, every outcome is predetermined. However, this does not imply that our choices lack significance. Within the confines of the block, the processes of decision-making and causality unfold authentically, despite their outcomes being defined in a timeless manner. The concept of free will could be seen as the way consciousness navigates its journey through a landscape that has already been mapped out. Reality would then take on the appearance of a completed film reel, its frames unchangeable, as our consciousness traverses them, crafting the vibrant illusion of spontaneity and transformation. Nevertheless, the enigmatic nature of quantum uncertainty shrouds the future in mystery. Quantum mechanics adds complexity to the block universe by presenting probabilities in place of certainties. Prior to observation, particles inhabit a realm of superpositions, embodying numerous potential states, and it is through measurement that they are compelled to settle into definitive outcomes. This uncertainty implies that the future may not be completely predetermined. In certain interpretations, every conceivable outcome exists at once within a vast quantum expanse, and what unfolds as the future is merely one strand among countless others. Even within a block-like structure, quantum uncertainty suggests that space-time may encompass branching possibilities instead of adhering to a singular, deterministic path. Experiments reveal that outcomes continue to elude prediction, regardless of the precision with which conditions are measured, suggesting that randomness is intricately embedded in the very fabric of the universe. In this way, relativity presents a finished geometry, while quantum theory introduces a glimmering aspect of openness, preserving the elements of mystery and freedom within the grand design of the cosmos. Watching a system can alter its trajectory. In quantum mechanics, the act of observation transcends mere revelation of information. It plays a crucial role in shaping the very nature of what is being observed. Particles exhibit wave-like behavior, characterized by probabilities, until an observation occurs, at which moment they take on specific states. The future of a system is shaped by the perspectives and timing of our observations. The renowned double-slit experiment illustrates this principle in a striking manner. In the absence of measurement, particles engage in self-interference, akin to waves, resulting in intricate patterns of potentiality. As one observes, the pattern disintegrates into distinct points, as if the particles were aware of the scrutiny they faced. This phenomenon suggests a profound relationship among information, measurement, and the very essence of reality. Observers are integral to the universe, actively engaging in its continuous development. Every observation subtly shifts the arrangement of space-time, intertwining awareness with the progression of matter and energy, revealing that knowledge and existence are inextricably linked within the cosmic tapestry. The connection between measurement and quantum indeterminacy reveals intriguing insights into the nature of time's progression. The process of quantum measurement shifts ambiguity into clear results, highlighting the distinction between potential events and those that have actually occurred. This shift might be what imparts direction to time. Prior to measurement, the system is characterized by probabilities that fail to differentiate between the past and the future. Once observation takes place, the outcome transforms into something unchangeable, contributing a fresh detail to the narrative of the universe. This transition from uncertainty to certainty mirrors the rise of entropy, as potential outcomes condense into actual occurrences. In this manner, every act of measurement evokes a feeling of progression, where the present stands as the dividing line between limitless possibilities and established facts. Some physicists propose that consciousness could be involved in this process, while others believe it is solely due to physical interactions. In any case, measurement acts as the link connecting the unpredictability of quantum phenomena with the structured reality that characterizes the progression of time. Space-time could emerge from the intricate quantum connections that exist between particles. Recent theories suggest that spacetime may emerge as a property constructed from quantum entanglement. As particles become correlated in specific manners, the arrangement of their connections may give rise to the geometry that is perceived as space and time. This concept turns the conventional perspective of physics on its head. Rather than viewing fields as existing within spacetime, one might consider the possibility that spacetime emerges from the very network of quantum relationships. Simulations and mathematical models indicate that the degree of entanglement influences the curvature of the resulting space, reflecting the way mass and energy shape geometry in relativity. If accurate, spacetime would not be an essential element, but rather a significant outcome arising from a more profound quantum framework. The distances we measure and the durations we experience reveal connections that intertwine microscopic systems. The universe unfolds as an intricate tapestry of connections, where its framework shapes the very dimensions that characterize existence. The universe might exist as a vast hologram emanating from its edges. The holographic principle posits that every detail characterizing the contents of a specific area in space can be inscribed on its external surface. This suggests that the three-dimensional universe we perceive could be an image derived from information held on a two-dimensional boundary. The idea emerged from research on black holes, where the quantity of information they hold seems to correlate with surface area instead of volume. Expanding this understanding to the universe suggests that all entities within it, ranging from galaxies to atoms, may arise from data inscribed on a far-off cosmic boundary. Investigations in theoretical physics and quantum gravity lend credence to elements of this perspective. As depth and distance unfold before us, they may reveal themselves as emergent properties, akin to the way a hologram conjures the illusion of three-dimensionality from a mere flat image. The universe can exist as both something you can touch and something that holds deeper meanings at the same time. The holographic principle implies that reality possesses layers of concealed complexity. If the universe is indeed holographic, what is perceived as solid and continuous space may be hiding a deeper informational framework beneath the surface. Much like a hologram that retains a complete image within each fragment, the universe might encapsulate its entire essence on cosmic surfaces. This viewpoint harmonizes the principles of gravity and quantum mechanics by imposing a restriction on the amount of information that can be contained within any given area of spacetime. Rather than being endlessly divisible, reality encompasses a limited number of bits that correspond to area. This framework offers insights into black hole entropy and may reveal important aspects of quantum gravity. It also prompts deep philosophical inquiries. If every physical phenomenon represents a manifestation of encoded data, then matter, energy, and geometry could be seen as various expressions of information. The depth observed in the universe emerges as an effect, indicating that reality encompasses both greater and lesser dimensions than it seems, constructed from patterns of pure information. Information could very well be the essential essence of the universe. From an informational perspective, all that exists can be understood as data. Particles, fields, and even space-time emerge as expressions of information processing, all under the influence of natural laws. This idea weaves together quantum theory, thermodynamics, and relativity into a cohesive framework. Energy may be understood as the ability to transform information, and entropy quantifies the extent to which that information is obscured or diminished. Research in quantum computing and black hole physics is progressively reinforcing this notion. Information cannot be obliterated. It can only be altered or hidden, suggesting that the universe maintains its complete informational essence throughout all processes. If true, reality emerges not from matter, but from the intricate web of relationships and codes, resembling a cosmic computation woven into the very fabric of space-time. The essence of existence emerges as the pinnacle of meaning, preserved and transformed through the continuous flow of universal information. Black holes hold the secrets of their contents on their surfaces, rather than within their vast volumes. As matter succumbs to the gravitational pull of a black hole, it does not simply disappear. Rather, its information is intricately inscribed upon the event horizon. This insight unravels a mystery that had previously jeopardized the very principles of physics. If information were genuinely lost, it would contradict the principles of quantum mechanics. Calculations indicate that the entropy of a black hole, reflecting the quantity of information it can hold, is directly related to the area of its surface. Every unit of area contains a fragment of knowledge about all that has traversed the horizon. This discovery connected gravity, thermodynamics, and quantum theory in an unforeseen manner, implying that these three elements are aspects of a singular, more profound reality. The surface of a black hole serves as a cosmic archive, preserving the history of its contents as patterns in space-time, guaranteeing that the universe's information endures even in the darkest depths. The entropy of a black hole is proportional to its area rather than its mass. Jacob Bekenstein and Stephen Hawking revealed that the entropy of a black hole is determined by the surface area of its event horizon, not by its volume. This indicates that as a black hole expands, its ability to hold information rises with the square of its radius, contrary to the cubic increase one might anticipate for regular matter. The connection unveiled a deep bond among gravity, thermodynamics, and quantum mechanics. It further established the groundwork for the holographic principle, which extends this idea to encompass the whole universe. The surface area serves as a crucial indicator of the amount of information encoded within the geometry of the black hole. This outcome suggests that the very fabric of space possesses a boundary when it comes to information. A limited amount of data can be contained within a specific space. The revelation transformed the way we perceive black holes and the essence of reality itself, implying that surfaces conceal more profound mysteries than their volumes suggest. Hawking radiation allows black holes to gradually lose mass and evaporate over time. During the 1970s, it was revealed by Stephen Hawking that black holes possess characteristics that prevent them from being entirely devoid of light. Near the event horizon, quantum effects lead to the spontaneous appearance of pairs of particles. One tumbles into the abyss, while the other manages to flee, taking with them a minuscule fragment of energy. Over immense timescales, this process enables black holes to shed mass and ultimately vanish entirely. The radiation remains exceedingly feeble for massive black holes, yet intensifies significantly for smaller ones as they approach the conclusion of their existence. This discovery brought together the principles of quantum theory, relativity, and thermodynamics into a single, cohesive framework. It also presented new enigmas regarding the fate of the information held within the black hole. Hawking radiation guarantees that even these cosmic abysses engage in the exchange of energy and information, demonstrating that nothing in the universe exists in complete isolation from the currents of physics. As they diminish, they release energy back into the fabric of space-time. As black holes emit radiation, they lose mass, leading to an increase in temperature and a subsequent acceleration of the process. Ultimately, the black hole releases its last remnants of energy in a final explosion of radiation, giving back what it had taken from space-time. This emission might unveil faint remnants of the information that once resided within, maintaining quantum coherence. The energy rejoining the universe plays a crucial role in maintaining its overall balance, affirming that nothing is ever truly lost. Although the specifics of this evaporation continue to be explored, it offers a captivating balance to the cosmic cycle of creation and dissolution. Black holes, previously regarded as the ultimate traps, emerge as active players in the renewal of energy throughout spacetime. Their gradual disappearance shows that even the most extraordinary entities adhere to universal principles, converting mass into light and nourishing the cosmos with echoes of their concealed narratives. The demise of a black hole releases information back into the cosmos. Upon the completion of a black hole's evaporation, the information it once contained must find a way to resurface within the emitted radiation, adhering to the principles of quantum law. The manner in which this occurs continues to be one of the most profound enigmas in physics, referred to as the information paradox. Numerous theories suggest ways to encode the missing data through intricate correlations found within the Hawking radiation. If accurate, this would imply that information is perpetually altered rather than obliterated. The process would reveal that spacetime serves as an impeccable record keeper, maintaining the integrity of its past. This insight links quantum information theory with the vast architecture of the universe, bringing together the tiniest and grandest domains of physics. The conclusion of a black hole, rather than a mere disappearance, could serve as a profound unveiling, returning to the universe the narrative of all that it had previously devoured. When all black holes have vanished, what will endure is nothing but spacetime. In a distant future, countless ages beyond what one can fathom, each black hole will have shed its mass through the process of Hawking radiation. The galaxies that once held them will have long succumbed to darkness, leaving behind only faint particles and radiation to endure. A vast, thin sea of energy will remain, stretching across the expanding fabric of space-time. In that distant time, even the tiniest quantum fluctuations would shape the vast cosmic scenery. As space-time stretches further, it will cool toward absolute zero, leading to a state where no structured matter can persist. The universe is destined to arrive at a condition often referred to as the heat death, a point where energy is evenly spread and all change comes to a halt. Even in this ultimate stillness, the fabric of spacetime will persist for a time, cradling the final traces of knowledge, the soft reverberation of existence, before it too might fade into an unknown realm, beyond the confines of our understanding of physics. One day, spacetime may also vanish, giving way to an existence of pure quantum nothingness. Certain cosmological models suggest that spacetime may not be everlasting. If it arises from quantum processes, it might also vanish when those processes conclude. As the universe approached its final moments, the fluctuations began to fade, and the very fabric of space and time threatened to disintegrate into a state devoid of geometry, duration, and distance. This quantum nothingness would not be devoid of substance in the usual way. Rather, it embodies a primordial potential, akin to that which once sparked the creation of the cosmos. From it, new universes could emerge, each possessing its own unique laws and dimensions. In this vision, existence unfolds in a continuous cycle where space-time emerges, evolves, and ultimately dissolves in an eternal rhythm. What seems like a conclusion may actually be a journey back to the origin, where existence lingers in a state of potential, poised for the next spark to set the intricate tapestry of life in motion again. The journey has come to a close this evening, a serene exploration through the intricate fabric of existence. As they journeyed together, they traced the intricate thread that connects space and time, observing its graceful curves beneath the mass of stars, its undulations in the presence of black holes, and its expansion alongside the ever-growing universe. Each movement, each glimmer of illumination, each fleeting moment is woven from that same unseen tapestry. It encompasses all within its tender framework, from the tiniest particle to the grandest galaxy. Allow your thoughts to ease into the tranquil cadence of the universe. Envision the subtle shimmer of starlight traversing vast expanses, the silence that lingers between galaxies, the gentle rhythm of time advancing steadily. One finds themselves within that same harmony, nestled in a universe that is expansive, timeless, and vibrant. If this peaceful journey brought you calm and wonder, please like, subscribe to Sleep Science Top 1, or share one thought below. What space-time fact surprised you most? Your support helps more sleepy souls discover this tranquil space. Breathe deeply, let go, and drift into dreams carried by the gentle curvature of the cosmos. Sleep well, dream deeply. Good night.